About in our daily lives, our physical experiences are typically predictable. We can assume that when we grab a cup of coffee and lift it off the counter, the force of our grip can do this job without us having to think too much about it. Of course, the unexpected can occur. But even then, our actions produce predictable results that can be described by using the same set of classical physical laws that Isaac Newton calculated centuries ago.
Newtonian physics is the body of physical law that emerged in the 1600s when Isaac Newton quantified what it means to describe the reality that we have access to. Objects have positions, they have speeds, and they're acted upon by forces. So in a construction site, when you see a construction ball swinging and smashing into things, Newtonian mechanics is the that allow us to calculate the trajectory of that ball, the impact that ball has when it smashes into the side of a building. So Newtonian physics is very much still with us. Sometimes people think about new ideas in science obliterating the past, making it obsolete, irrelevant. That's not the case. Even though we have refined Newton's ideas in the domain of quantum physics or in the domains of relativity too, in everyday situations that we human beings typically encounter, like a construction site or anything else you see when you walk around in everyday life, Newtonian physics is a spectacularly good approximation to describing what's actually going on. If you take any macroscopic situation, construction site, whatever, and we're able to shrink it down smaller and smaller and smaller until it became on a size on par with atoms, 10 to the minus 10 meters or so, then at those tiny scales, every process is going to amplify and reveal the quantum nature of the universe. So for instance, you could have a wrecking ball heading toward a wall that it's trying to smash through. And in the quantum version of that, the wrecking ball could actually pass right through that wall without smashing it at all. It could tunnel right through it. Quantum tunneling. And it could quantum tunnel back. Something that would be utterly absurd in any ordinary situation. But in the microscopic domain, these kind of weird things would be part and parcel of what happened all the time.
What's happening at that subatomic level, where atoms are only 10 to the minus 10 meters or so? The level of quantum mechanics.
Quantum mechanics is the body of physical law developed in the early part of the 20th century by a single generation of physicists in order to have an accurate description of how particles behave in the microscopic realm.
If you thought an atom looked like this, you would be wrong. Electrons don't orbit the nucleus like planets zipping around the sun.
You would have thought, if you were a physicist at the time and didn't know about quantum mechanics, that electrons should behave like little baseballs, right? They're just little particles. We have the laws that govern the big versions, and those laws should be the same laws that govern the small ones. The data showed that that was not true. The data showed that if you use Newton's ideas in the realm of particles, you'll get wrong predictions.
If we were to apply Newton's laws to the atomic world, the electrons would collide into the nucleus and self-destruct every fraction of a second. Instead, electrons behave more like vibrations, each with its own frequency.
Now the laws of quantum physics come into the story because you've got electrons that are in quantum clouds surrounding the nucleus of the atoms that are making up that particular object. And to understand those structures and those properties, you need new equations that Isaac Newton didn't know about.
In 1894, physicist Max Planck was hired by the German Bureau of Standards to help design a better light bulb. Planck investigated the qualities of heat energy and light in a series of experiments. As a light bulb filament heats, its color changes from red to yellow to white. But why doesn't the light get bluer at the higher end of the spectrum when more energy is applied? Planck made a groundbreaking assumption that energy is not delivered in a continuous wave, but in packets, or quanta. And these quanta are uniquely and mathematically proportional to a given frequency. This means that certain frequencies only hold certain amounts of energy. The new understanding of packets, based on Planck's observation, described a new physics. Planck received a Nobel Prize, and quantum mechanics was born. In 1905, a young patent clerk named Albert Einstein published 4 papers that upended the field of physics. Einstein may be best known for his theory of relativity, but it was his paper on the quantum mechanics behind the photoelectric effect that eventually earned him his Nobel Prize. The photoelectric effect happens when light is shown on a metal surface, and electrons are given enough energy to escape. So, using Planck's formula, Einstein proposed that only certain wavelengths can carry enough energy to release electrons, regardless of how intense the light is. Therefore, light energy is emitted in wave packets, or photons. But can a single photon of light also be a wave? The double-slit science experiment shows us how.
In one single experiment, the double slit experiment, you can see the heart of quantum mechanics laid bare. And the experiment begins like this. We have a barrier with 2 openings. It's called the double slit. And we begin by firing large objects, pellets or BBs, at this barrier. And as you would expect, those BBs that go through the right slit will land in a band on the right aligned with it. Those BBs that go through the left opening land in a band aligned with it on the left. Now we're going to make one adjustment to this experiment. We're going to take those projectiles, those little pellets or BBs, and we're going to dial down their size, making them smaller and smaller and smaller until they are as tiny as little particles, electrons. And we're going to do exactly the same experiment. Now you would think that if we fire